Okay, here's 1.2. It is called Transformations of Linear and Absolute Value Functions. All right, so here we've got an equation, and if I put this in function notation, it's going to look basically the same, except we have f of x instead of y. All right, and so it's really important that you understand how function notation works in order to understand these transformations, at least from the equation side of things. All right, so here we've got this function, the same function I just wrote over there, and we're going to find f of 5. So what that means, my input is the x here. And so now when I have f of 5, I'm writing function f with an input of 5. So the input is where the x goes. So that just means I'm going to replace the x in 3x minus 1 with 5. And then simplify. So I'd have 15 minus 1 there, and that's going to equal 14. So f of 5 is 14. Okay. On the next example, here I have f of x plus 2. So I have function f with an input of x. So I'm not changing the input of function f here. What I'm going to do instead is substitute. I'm going to substitute f of x equals 3x minus 1. So that means I can take 3x minus 1 and substitute it in for f of x. So anytime I substitute something, I use parentheses. It's going to help out a lot if you don't skip doing that. And then when I simplify this would look the same without parentheses. And then I'm just going to combine negative 1 and 2. Negative 1 plus 2 is positive 1. So that means f of x plus 2 is going to equal 3x plus 1. Okay? That's not the same as adding to the input. This one's going to be different than part B. So this means I'm taking function f with an input of x plus 2. So if you look at this function, f of x equals 3x minus 1. I'm going to think of that as 3 times something minus 1. 3 times something minus 1. I just left blank parentheses. And my input, instead of having x in that position, I'm going to replace it with the quantity x plus 2. And it's really important to use parentheses when you substitute here, especially because the next thing we're going to need to do is distribute the 3. Often, when people don't use parentheses, they'll forget to distribute. So here I have 3x plus 6. Still got the minus 1 at the end, and then I'll combine the 6 and the negative 1 into 5, like so. Okay. All right. So now let's look what happens when we add some negatives into the mix. So here I'm going to take the opposite of f of x. So I'm going to substitute for f of x just like I did on part B. So I'm taking the opposite of all of this. A lot of times I'll see people do, I'll take the opposite of 3x minus 1. So there we go. So they just put a negative in front of the 3x minus 1. But we're taking the opposite of the whole function. So again, you need to use parentheses when you substitute because we're going to have to distribute that negative. We're multiplying, taking the opposite of both these terms. You can think of it as multiplying both terms by negative 1. So this is actually going to be negative 3x plus 1 because we're taking the opposite of both terms over there. Okay? And then here we're taking the opposite of the input. So I'm going to change the input to negative x. So 3 times something minus 1. My something is going to be negative x. And then when I simplify this, 3 times negative x would be negative 3x. And there we go. So I just replaced the x with negative x on that last example. Okay. All right. So now that we've got a little review with function notation, let's get into some different types of transformations. A transformation is just a change, right? And one thing you can do to a graph, let's say this is a graph of a line, I can shift it left or right, like so, or I could move it up or down, like so, and those are called translations. So in this little chart I made, this top row, these are all going to be translations. Okay, these ones up here. Here, so I'll separate this like so. Okay, so those are shifts. So we're shifting things either up or down or left or right. Okay, when we're adding or subtracting to an input, that's actually going to move things left or right, and it might go a little opposite to how you might think. When we're adding something to the input, we're actually going to go left whatever h is. So I'm going to say left h. Okay? When we have this version, when we're subtracting from the input, we're going to go right whatever h is. Okay? So when we're talking about input, adding is left and subtracting is to the right. Okay? Now we're on these two, we're not adding or subtracting to the input. We're adding and subtracting to the output. F of x is called the output. So we're adding or subtracting outside of the parentheses, and that means we're going to move things up or down. So when you're adding, it goes up h, and when you're subtracting, it's going to go down h. So those are all translations. Okay? These other twos, when we're multiplying by a negative, we're going to get a reflection. So when you're multiplying the input, this is going to reflect over the y-axis. Okay, and then when we are multiplying the output, the whole function by -1, then we're going to reflect over the x-axis. Okay, so using this little chart we just put together, let me separate this out like so. Using this little chart, let's look at some examples here. So this says write a rule for g of x for, and then we've got a translation 5 units to the left of f of x. So I'm going to write a new function called function g, where it's function f, but it's moved 5 units to the left. So I'm looking up here, 5 units to the left. Okay, so I'm going to have to add something to the input to move left. So my new function g is going to be f of x plus 5. Adding to the input would move it to the left. Okay, so g of x is going to be a transformation then, of a translation to be more specific, of function f. Okay, so then I want to simplify this. I want to figure out, well, what does f of x plus 5 equal? Well, that means I'm going to function f and I'm going to input x plus 5. So this says 2 times something plus 3, and my something is going to be x plus 5. Okay, and then let's start to simplify that. So I use parentheses again there because I'm going to distribute. And then I can combine the like terms, and I'm going to get 2x plus 13. Okay, so function g then would be equal to 2x plus 13. Okay, all right. So now let's do a reflection of f of x over the x-axis. So I'm looking, okay, going over the x-axis, this is what we got. So g of x is going to be the opposite of f of x. All right, and then I'm going to distribute, not yet, I'm going to substitute is what I meant to say. So I'm going to replace f of x with the quantity 2x plus 3. And when I substitute, I'm going to use parentheses that I don't forget to distribute that negative. Okay, so this is going to give me negative 2x minus 3. So g of x is going to equal negative 2x minus 3. Okay, all right, let's go over the y-axis now. So over the y-axis, we're going to change the input to negative x. So g of x is going to equal f of negative x. Okay, and that just means we're taking function f with an input of negative x. So 2 times something plus 3, and that something is going to be negative x. And when I multiply here, I'm going to get negative 2x plus 3. Okay, so g of x is negative 2x plus 3. Okay, so we've looked at some translations and reflections. Let's look at some stretches and compressions. These are a little tricky. Compressions, by the way, are sometimes called shrinks. So the Big Ideas books calls them shrinks, but I'm used to calling them compressions. Okay, so let's talk about what this is first off. So So let's say we have an absolute value function. It's going to look like a v, and a stretch or compression is going to change the width of the v. So if let's say we have a horizontal compression, a horizontal shrink, that means these points are going to move in towards the center horizontally, and that would end up with a narrower one. A horizontal stretch would be like open up like this because the points would move outwards. Okay, and you can also have the points move up or down. That's going to be with a vertical change. Okay. All right, so let's get into this. So this is going to happen when we're multiplying the function by something. We can multiply the entire function by something, which would give you a vertical change, or you can multiply the input by something, and that's going to give you a horizontal change. Okay. So our two types we've got a vertical stretch and a vertical compression. All right, so the way you can tell which one you're going to get is by the value of a. So if a is greater than 1, then we've got a vertical stretch, and if a is less than 1, we're going to have a vertical compression. Now technically, it could be greater than 1 or less than -1. So this is technically the absolute value of a, but you can just think is a greater than 1 or less than 1. And I'll get into that in a second here. But what we're going to do is write g of x for a vertical stretch of f of x by a factor of 5. Okay, so the factor is what we're going to be multiplying by. All right, so here we're going to write function g. All right, and I know I'm going to be multiplying on the outside like this because that's how I would do a vertical change. All right, so in this one I'm going to put 5 times f of x, and hey, we've got a number more than 1, right? So that would give me a vertical stretch, and it says we want a vertical stretch there. Okay, so then when I'm going to substitute in for f of x, I'm going to take all of this. That's what f of x equals. Now, I have to use parentheses when I do that, and it seems a little weird, maybe, but it's not just as simple as putting a 5 in front of the absolute value symbol, okay? Because we want to multiply the whole function by 5. So I'm going to have to distribute this 5, and here's how I'm going to distribute it. I'm going to distribute it like that. You can't distribute into the absolute value function, but you can put a 5 right there, and then we're also going to multiply the 3 by 5. Okay, so I've got then 5, and I get the x minus 2, and 5 times 3 is 15. Yeah, and I often see people distribute into absolute value, but you can't do that. So that's as far as we can go. Okay. All right. So when we've got a vertical change, the factor is the same as the a value, and it gets a little confusing because on the horizontal ones it doesn't quite work like that. Okay, so let's look at our two brands here. We've got a horizontal stretch and a horizontal compression or shrink. I'm starting to abbreviate a little bit to make this go a little quicker. All right, so if a is less than 1, then we've got a stretch, and if a is greater than 1, we've got a compression. It's confusing because it's kind of backwards from how it was with stretches and compressions over here. And again, technically, this is the absolute value of these things. Okay, so this says write g of x for a horizontal stretch of f of x by a factor of 3. So okay, we got function g. So I'm doing this in red because I'm going to purposefully make a common mistake here, okay? And I totally understand why you would do this because, hey, we've got a number inside the function now, right, in the input. So, hey, 3. So I see a lot of people do this and then figure out what f of 3x is. The problem with that is that my a value here is going to be more than 1, which actually give me a compression, not a stretch, okay? So this is going to be incorrect. So you might think that A would be 3, but it's not. It's actually going to be the reciprocal. So A instead is going to be 1/3. So the reciprocal means you flip it upside down in fraction form. So 3/1 would be 1/3. So I'm going to use 1/3 as my input, okay? And you always have to use the reciprocal of the factor when you're doing stretches and compressions, or horizontal stretches and compressions, I should say, okay? So this is going to be f of 1/3 x, all right? Very confusing because you do different things depending on if it's a vertical or horizontal stretch, and it just takes a little getting used to, okay? So then I'm going to substitute this into function f. So I'm looking at function f, and I'm going to replace the x with 1/3 x. So good news is there's not much to do in terms of simplifying. I didn't use parentheses there to substitute because there's no simplifying to do after that. So there's my function. Okay. All right. Let's try some more. So this next one, write g of x for a vertical stretch of f of x by a factor of 4. So on the vertical side, the factor is the same as the a value. Okay. So, all right, g of x, and then I'm looking, this is a vertical stretch, so I'm over here in this column with a vertical stretch, so we're going to be multiplying on the outside, and this is a number more than 1, so I'm going to do 4 times f of x, like that, right? I wrote it in parentheses, but, and then I'm going to substitute. So f of x is, I almost looked at the wrong one, is all of this. And again, I use parentheses there because I want to remember to distribute the 4 in those 2 spots. So g of x is going to be 4 times the absolute value of x plus 2 minus 5. Okay. All right, so now we're going to do a horizontal compression. And remember with the horizontal ones, if the factor is 3/5, that means A is going to be the reciprocal of that 5/3, okay? And then with the horizontal ones, we're also multiplying the input by whatever number. So g of x here is going to be f of 5/3 x. Okay, so then I'm substituting into function f, right? I'm writing function f with an input of 5/3 x. So I'm going to go replace the x here with 5/3 x. Okay, and I know I've been saying that you should always use parentheses, but if I put parentheses around 5/3 x, there's not going to be anything else to do there. So that's why I skipped that there. Okay, so there is my new function. Really tempting to use 3/5 instead of 5/3, but you gotta be on the lookout anytime it's horizontal. Use the reciprocal of the factor. Okay. All right. Write g of x for a horizontal stretch by a factor of 8, followed by a translation 10 units down. So this is a two-parter. We got 2 different transformations here. So I'm going to do it piece by piece. So I'll first say, even though ultimately I'm going to say that this is function g, first I'll just do my horizontal stretch. Just kind of keeping track of what I'm doing here. I'm going to call this function h, just to show that this is, I'm only going to do the horizontal stretch here, okay? So a horizontal stretch by a factor of 8. With the horizontal ones, we want to use the reciprocal as a, and then we're going to multiply the input by your a value. So this is going to be f of 1/8 x. Okay, and so let's see. I'm going to input into I'm going to write function f with an input of 1/8 x. I'm going to replace the x with 1/8 x. Okay, so there's step one. I've done the horizontal stretch. Now I'm going to do the translation. Okay, and after I do the translation, this will be finished. So I'm going to say that this is going to be function g. So because I'm going to work on function h. Okay, so I'm thinking, okay, if I wanted to translate this 10 units down, then I'm going to take h of x and subtract 10 like that on the outside. If you subtract on the inside, you'd actually be moving it to the right. That's not what I want. I'm moving down. Okay? So then I'm going to substitute h of x was all of this, right? So I'm substituting here. Got all of that, and then I'm subtracting 10 from the end. This would actually look the same without parentheses, and then I just need to combine the 1 and the negative 10. Okay. Problems like this, when there are multiple transformations, do them in the order they're listed in the problem. Sometimes it'll work out if you do them in the reverse order, but it'll always work out if you do them in the order they're listed. Okay. Okay, this section is one of the toughest ones, I think, in the book, and it's right at the beginning of the book. But we got a lot to do here, so we're going to get in. We haven't touched the graphing side of things yet. So let's get to that. So I've got 3 different lines graphed here. Y equals x, y equals 2x, y equals 1/2 x. If you notice, when you increase, if the a value here is 1/2, 1, and 2, as you increase the a value, the line's going to get steeper, right? So the same thing is going to happen with absolute value functions. An absolute value function would look like a v, but what we're going to have, if you were to draw in the other side of this, say you had y equals x, it's going to look like this, okay? And when you have y equals 2 times the absolute value of x, it's going to get narrower like that, right? So you'd have the other side of this. And same thing, this would be the 1/2. So the moral of the story here, I was trying to show that when you have a value like 2 as your a, your v is going to get narrower. Okay? And when you have a number less than 1, like 1/2, it's going to get wider. And it doesn't matter what the placement of the a is, whether it's inside the absolute value or on the outside. Okay? So looking at these down here, these are parent graphs. So this would be like y equals x on that side, and this would be y equals negative x on that side. Together they make that v, and this is going to be an absolute value function. Okay? So what I'm going to do here is make a little chart. I'm going to split this into 4 sections. Like so. Okay? And I'm actually going to close this off. Like so. All right. So, oh, sorry. Let me back off a little there. All right. So let's make these we're going to do some horizontal changes in this column, and we'll do the vertical ones here. Okay, and we can have this top row be stretches, and this can be compressions or shrinks. Okay, all right, so all of these y equals absolute value of x is already graphed. You don't need to write it in all of them, I suppose, but I'm just going to compare these changes to the parent graph, okay? So if we've got a horizontal stretch, you might see something, and this is just an example of a horizontal stretch. You have a number on the inside, okay? That makes it horizontal, and then when you have a number less than 1, it's going to make it wider, okay? And when we go down to horizontal compression, we'll also have a number on the inside, and I'm just going to use 2 there, but that number, the a value, be more than 1, okay? So let's look at what would happen with a horizontal stretch first. So this is going to get wider because these points are going to move out. That's what a horizontal stretch is. They're moving horizontally out away from the center of the graph. So if you look at points B and C, they're 1 unit away from the center. So I want to double that here so that now these are 2 units away from the center of the graph, from the y-axis, okay? And points A and D are 2 units from the center, so I want to double that. Often I'll see people put A and D here and here, but I want to double that distance from the center. And those are my new points, okay? So I'll call this A prime because that's my A after the transformation. And there's all the prime points, okay? So if you draw this in now, and the vertex is going to stay in the same place, but if you draw it in, it would look something like this, okay? And so I doubled those distances because this was 1/2. If it was 1/3, I would have tripled the distance from the center, or if it was 1/7, I'd multiply by 7, okay? So here my A value is 1/2, and the factor is going to be the reciprocal of that. So the factor is actually 2. The factor is what I'm multiplying the x coordinates by. So I'm doubling the x coordinates so that they get twice as far from the center, okay? So let's look at the horizontal compression then. So here the A value would be 2 again, or sorry, not again, but A is 2, and the factor is going to be the reciprocal of that. So when you multiply these x coordinates by 1/2, they're going to get closer to the center. So points B and C would end up here and here, and points, the half unit from the center, right? Points A and D are 2 units from the center, so I want to take half of that, and then we're going to have a graph that looks something like that, okay? Which makes it narrower, right? Okay, so let's look at these others. That's when we're multiplying on the inside, we get a horizontal change. When we're multiplying on the outside of the opposite value, we're going to get a vertical change. Okay, so multiplying on the outside, vertical change. The 2 would make it narrower, so to get a narrower V here, it would have to be a vertical stretch. Okay, so in this one, A is going to be 2, and then the factor is also 2. So again, it's confusing because you don't take the reciprocal with the vertical ones, but you do with the horizontal ones. All right, so these points, when we're moving vertically, that means these points can only move up or down. So here they're going to stretch up. I'm going to move all of these points up. So I want to double the height of these points from the vertex. The vertex stays put, but points B and C, when I double their height, they would be there, right? And then I don't want to put D here. I want to double the height. It's 2 units above the x-axis, so let's double that. And same thing with A. Okay, and there's what y equals 2 times absolute value of x looks like. All right, and then here my A value is 1/2, and the factor is also 1/2. And so these are moving vertically, but if I move this up, it's going to look narrower, right? Those points up like I did up here. I'm actually going to move them down, which is going to kind of squish my V. It's going to look wider then. So I want all these points to move down, and I want them to be half the height they are right now. So points A and D will end up 1 unit above the x-axis. Points B and C will end up a half unit above. And then I've got my vertical compression or shrink. Okay, so you might notice these two look the same. Those two look the same, but it is important because when we get more complex functions, it makes a difference if you're getting a wider shape with a horizontal stretch or a vertical compression or shrink. They're not the same thing. Okay, so now let's try some actual graphing of absolute value functions that have stretches and compressions. So here's my advice when graphing these types of problems. First, find and plot the vertex, because once you get that, it's going to stay put, at least with the method that I use. So you won't have to move it around. And then we're lightly going to graph what I call the ghost. and that's just something I made up, but that's my function without stretches or compressions. So I'm going to pretend it doesn't have a stretch or compression, even if it does have one. But I do want to include any reflections. And really all I'm looking for with the reflections, some of these will open downwards if you've got a reflection over the x-axis. You don't really need to worry about the reflections of the y-axis because the way I find the vertex takes care of that. Okay? And then the last thing we're going to do is graph the 5 critical points. So we're going to take our ghost points and do the stretch or compression on the ghost points. Okay, and I'll show you how all this works on this example. So first thing I'm going to do here is look for the vertex. Some people are going to look at this and say, oh, the vertex is -3, -2, but that's incorrect. That's not the vertex. Because it's not as simple as just changing the sign of this. What you want to do is take the whole contents of the absolute value, set it equal to 0, and then solve for x, and that's going to give you the x coordinate of the vertex. So I'm going to subtract 3 from both sides. Okay, and then to solve for x, I'm going to double the equation. I'm going to double both sides, because 2 times 1/2 is 1, so then I just have x equals -6. So my x coordinate is -6, not -3. Your y coordinate is whatever is added or subtracted to the end. So my vertex then is going to be the point -6, -2. Okay, so once I get that, I'm going to plot that on my graph, -6, -2, there it is. Okay, that's my vertex. I'll just label that because that's going to stay put. And then I'm going to lightly, actually I'm just going to make the points and not draw in the, I'll do it with a dashed line since I'm using pen here. So if this would be opening upwards because it doesn't have a negative in front of the absolute value, and the 1/2 is going to make it wider or narrow, but we'll get back to that in a second. My ghost, I'm just thinking, okay, what would the parent graph look like if it was starting in this vertex opening up? I go up one to the right one, up one to the left one, and continue that pattern. So this is what I mean by the ghost points. Okay, so with no stretch or compression, this is what we'd have. Be a lot easier problem with no stretch or compression, but we still have to do the stretch or compression. Okay, so that's where the 1/2 is going to come in. So first thing I like to think with this is, well, would that give me a wider or a narrower v? Okay, and since it's a number less than 1, it's going to be wider, so that's good to know. Now, it's not a technical term. We still have to figure out, well, do we have a horizontal or vertical stretch or compression? Okay, so the next thing I'm going to look at is I want to figure out if it's horizontal or vertical. Now, the 1/2 is touching the x. It's multiplying the x directly. The x-axis is the horizontal axis, so that's how I remember, well, if that a value is inside, then it's going to be a horizontal change. Okay, so I know I've got a horizontal change. That means these points can only move left or right. The vertex stays put, but the other points are going to move left or right. They're not going to move up or down. So then to figure out if it's a stretch or compression, I'm going to put these two things together. I'm going to think, okay, if they can only move left or right, if I move them in, this would get narrower. I don't want to move them in, I want to move them out. So I want them to stretch horizontally away from the vertex, so from the middle of the V. So that means it has to be a horizontal stretch. Okay? So now I'm looking at the factor, it's 1/2, so that means I'm going to double the horizontal distance from the vertex. So this is 1 unit away. I want to double that. And these 2 points are 2 units away. There's the middle of my V, right? Those are 2 units away from the middle. So horizontally, I want to double that. Okay, and there's so these are my 5 critical points, the vertex and 2 other points. And there we go. Okay, all right, let's try another. So here we've got the vertex. Well, x plus 2 equals 0, so x equals -2, and then there's my y. So the vertex would be -2, -1. -2, -1, there it is. This one's going to open upwards because it doesn't have a negative out here, right? So then here are my ghost points. Okay, and now I want to deal, so that's what it would look like with no stretch or compression. Whoops. And then I want to deal with the 3. So now I'm thinking, okay, a number more than 1 is going to give me a narrow V. Okay. Now this, I need to figure out horizontal or vertical. It's not touching the x. It's on the outside of the opposite value. So if it was inside, it'd be horizontal. This means it's going to be vertical. So that means these points can only move up or down. Well, if they move down, it would look like it's squashed. It would be wider. So I want to move these points up. Okay, and this time, since it's a 3, I want to triple the height of those points. So those first 2 points are 1 unit above the vertex. If I triple that, now they're 3 units above the vertex. Above the vertex, not above where they were, right? It's 3 units above. And so these are 2 units above. If I triple that, that's 6. So 1, 2, 3, 4, 5, 6. So then those points will go there. And now we've got a narrower V by way of a vertical stretch. Sorry, I forgot to write that this is stretch here. Okay, that's the end of the lesson, and I'll see you next time.